Hello friends, welcome you all. In last lecture, we are discussed the requirements of good aggregate, then the classification of aggregate according to source, size and shape. Now, in this lecture, we are going to discuss the impurities in the aggregate. Okay, so what are those impurities? Let us see. Aggregate that contains the excessive amount of tannic acid or vegetable matter or oil or human acid or sulfate or carbonic acid, alkali salts are considered to be harmful. This presence of these harmful substances prevents the proper adhesion of cement on the surface of aggregate and thus affect the properties of concrete adversely. So these impurities are further classified as organic impurities and inorganic impurities. In organic impurities, it contains the decayed vegetable matter or organic clay, then decayed animal matter. So it affect on the setting time and the strength of concrete. So if organic matter exceed the limit, then the fine aggregates is either rejected or it is completely washed before using. Then inorganic impurities mainly contains the silt and clay. This clay and silt if exceed can be easily removed by washing the sand. So these some following impurities we see may be present in the fine and coarse aggregate individually or in combination. So first is silt and clay, then decayed vegetable matter and humus, salt, stone dust, coal and lignite, mica and shale. So these all impurities present on in aggregates, both fine or coarse aggregate individually or in combinations. So what are the effect of these impurities in the aggregate on concrete? Let us see the effect of impurities in aggregate on concrete. First, that is silt and clay. These silt and clay impurities mainly present bond between the aggregate particles even with the higher water cement ratio. Hence, concrete weakens proportionally. So, before using the impurities or before using these aggregates, the impurities on the aggregate, that is silt and clay, should be washed thoroughly. That is, aggregate should be washed thoroughly, so these impurities will be removed. Okay. Next is the decayed vegetable matter. Decayed vegetable matter presents the process of the hydration and reduces the strength of concrete. Okay. Next is the salt. Salt, the hygroscopic nature of this salt causes the efflorescence. Efflorescence means the some slightly white particles we are seeing on the surface, okay, of the concrete. Then, and it is unsightly appearance. It affects the setting properties and the ultimate strength of concrete. Next is the stone dust. If this is present in excessive, this dust result in the segregation and bleeding in fresh concrete, and it reduces the strength of the concrete as well. Segregation means the particles are segregated, okay, means paste and the sand or the aggregate is segregated from each other, and bleeding means there may be a cement placed float on the surface of the concrete. Okay, so this stone particle, if it is in excessive, then it reduces the strength of concrete as also. Okay, then coal and lignite, the impurities reduces the hydration and the bonding of aggregate particles. It found responsible to the decrease the strength and durability of concrete. And lastly, the mica and shale. These deleterious materials means harmful materials. Okay, also affect the concrete strength. And this mica reduces the strength and durability considerably, while shale gets the swell when wetted, and it results in pitting in concrete. So these all is the effect of impurities if it is present on the aggregate or in concrete. Okay. So next point is the grading of aggregate. So what is meant by grading of aggregate? So it is the analysis of size of aggregate particles available in the given sample by sieve method. We can call it as grading of aggregate. These aggregates comprise about the 55% of the volume of mortar and about 85% of 85% volume of mass concrete. Okay, so it well known that the strength of concrete is dependent upon water cement ratio, provided the concrete is workable. Concrete is workable. So the important factor for producing workable concrete, the grading of aggregate should be good one. Okay, so this grading of aggregate implies that the sample of aggregate contains all standards fractions of aggregate, okay, in required proportions such that the sample contains minimum voids. Okay, and it is further classified as the well graded aggregate, uniformly or poorly graded aggregate, and lastly the gap graded aggregate. So let us see what is meant by well graded aggregate. The aggregate sample which contains particles of all sizes, that is finer to coarser in it, such sample we can say well graded aggregate. Or if we are defined as, we can also define it as, if the particle of all sizes are present in the appreciable proportion, then it is called as a well graded aggregate. Okay, so for good concrete work we require these well graded aggregates which provides the minimum voids. Okay, which contains minimum voids. Next is the uniformly graded aggregate, or we can call it as poorly graded aggregate. Okay, the aggregate which contains particles of spatially same or uniform size in it. Okay, such soil is considered as uniformly graded aggregates. So in the aggregate, if the particles are of almost same size, okay, means if we are taken the one sample, that is 500 kg sample, in this sample we are getting the aggregate size of same, that is suppose all the aggregate of 20 mm and 10 mm size. Okay, so we can call as it is a uniformly graded aggregate. Okay, next is the gap graded aggregate. It is the aggregate in which particles of any specific sizes are available and other sizes are totally absent. Such sample be termed as gap graded aggregate. Okay, so if a particular sieve size is not present in the aggregate, okay, they are called as gap graded aggregate. Okay, such sand which has a gap grading is generally not preferred to the sand which is uniformly graded. Okay, so gap graded aggregate creates deficiency in the cohesiveness and permeability of the surface finish. Okay, so for good concreting work we require the well graded aggregate, or we are avoiding this uniformly graded or gap graded aggregate. Okay, so next is the properties of fine aggregates. Okay, so what are those properties? Let us see. First, size, second, source, third, shape, then the moisture content, then the cleanliness, then bulk density. Bulk density means what? The density of aggregate considered along with the volume of voids between the particles, then the fineness modulus, then specific gravity, then silt content, and lastly bulking. So let us see some of the uh, physical properties of the fine aggregates. That is the first, fineness modulus. Okay, and this fineness modulus of fine aggregate we are calculating by using the sieve analysis. Okay, so firstly, what is meant by this fineness modulus? It is defined as the ratio of sum of cumulative percentage of weight retained on the various IS sieves taken up to a 150 micron sieve divided by the empirical constant 100. Okay, so this fineness modulus we are getting by the ratio of cumulative percentage weight retained on the IS sieves. Okay, that is up to the 150 micron IS sieve. Okay, we are not getting, we are not getting into account the 75 micron and pan. Okay, we are taken the up to the 150 micron IS sieve. Okay, So the cumulative percentage of weight retained on the IS sieves up to the 150 micron divided by the 100, we get the fineness modular. Okay, here you can see the some different sizes of sieves. We are arranging in the descending order. This is sieve shaker. Okay, so what is the procedure of this uh, calculating the fineness modulus? So firstly we are arranging the set of IS sieves, that is 4.75 mm, 2.36 mm, 1.18 mm, 600 micron, 300 micron, 150 micron and 75 micron, and lastly pan in descending order, okay, with coarser sieve at top and finer sieve at bottom. Okay, here we are seeing the fine aggregates, so the maximum particle size should be a 4.75 micron. Okay, we are knowing the what is meant by fine aggregate, the size, the particle size having the less than 4.75 mm we are calling as fine aggregates. So we are arranging these IS sieve in a descending order. Okay, that is coarser sieve at top and finer sieve at bottom. Second, then take the oven dried fine aggregate sand. Okay, sample about 500 gram. Okay, we are taking the oven dried sample. Okay, for this oven dried sample we are kept the temperature 110 plus minus 5. Okay, so take a 500 gram of sample, that is oven dried sample, then put it on the topmost sieve, then place lid at top and pan at bottom. Okay, of sieve that of sieve set respectively. Then keep this assembly on the mechanical sieve shaker or electrical sieve shaker and shake it for 15 to 20 minutes so that this sand will be completely sieved. Okay, then this take the weight of the sample fraction written on the each sieve separately and calculate percentage finer using the following format. Okay, like this is the sieve size in mm, here 4.75 mm, okay, 2.36 mm, 1.18 mm, right, in a descending order. Then weight written on that particular IS sieves in grams. Okay, we are writing here. Then weight, percentage of weight retained. Okay, it is calculated by the weight retained divided by the total weight of that sample multiplied by 100, we get the percentage weight retained. Okay, then lastly we are calculating the cumulative percentage weight retained. Okay, and we are adding this, that is we are taking the sum of this cumulative percentage weight retained. Okay, and divide it by 100, we get the fineness modulus of that sum. Okay, then we are classified this sand on the basis of this fineness modulus is fine sand if this fineness modulus in between 2.2 to 2.6 we are calling as fine sand. If it is in between 2.6 to 2.9, then we are classified as a medium sand, and if it is in between 2.9 to 3.2, we are classified as a coarser sand. Okay, so hope you will understand today's session. That's it for today's session. Thank you.